So we've now talked about this in theory, and we're going to do an example. So we have here, this is not quite a diagram yet because it doesn't have the cartoons, but it's close. We have a person who weighs 50 kilograms, or with a mass of 50 kilograms, standing on a log that is 3 meters long and weighs 30 kilograms, or has a mass of 30 kilograms, and it's resting on 2 rocks at the ends. And the person stands 2 meters from the left side of the beam, which leaves 1 meter from the right side. So I draw in those values. I write 30 kilograms, 50, 2 meters, 1 meters. And our question is, what are the support reactions at the 2 rocks? So first I'm going to diagram this, then indicate the forces and moments, then clarify the unknowns. So I'm going to start by writing my support reactions. I'm going to do the logic on this slide, going right over this. So my rocks, I tried to sort of draw this idea there that the bar could rotate at that point, but if there's enough friction from the weight, it's not going to move sideways, and it certainly can't move up and down because it can't move down because it'll knock into the rock. So these sound like pins, so I'm going to put pins here. Now, by convention, that one of these we are going to show as a roller. And the reason we do that is because if the beam, if it starts to bend, the 2 ends go towards each other, but the amount is so small that it's generally allowed. The friction wouldn't prevent that little tiny bits of movement. And so that roller indicates that there can be small movements in that direction, and that it's not being stretched by those rocks to prevent bending. So there I've got my pin in my roller indicating my unknowns, which also tell us then that we are going to have an unknown here, and I'll call this the A point. And I think I'll actually indicate this place the person is as B, and the place here as C. And so this is an unknown in that should be C. That's the unknown in the C. This is the unknown support reaction in A. And because there is technically one here, FA in the X, but if there's no other forces in that X direction, we can kind of leave that out. We'll come to that, but I'll leave it in for now so I can have that explanation. Okay, so now we also have a downward force here where they are standing that's a known force, and we can call that the force at B, and that is going to equal the 50 kilograms. So remember, mass times acceleration is force times G, where G is the 9.8 meters per second squared. That's the acceleration due to gravity. And then the last thing we're going to have here is the fact that we have a distributed load across this beam. Now, I can save time here. That this beam is uniform here, and we're already told what the total force is, which is 30 kilograms times G. So I don't really need to figure out force density. That's unnecessary to do. I just need to find out where that's applied. And because this is symmetric, it will be applied at the midpoint. I can draw this on the top or bottom. Right here, I'll draw it on the bottom just because there's more room, or maybe because you like to think about it as being pulled down. But it's 30 kilograms times G. And we now have these additional distances of 1.5 meters that we can draw in here because it's at that midpoint due to symmetry. So I have drawn there my diagram right over the old one, and then we'll go on to the next one to start. And I've indicated forces and moments. And I guess the last step here is to clarify the unknowns, and you can do this any way you want. Right now, I'm just going to rewrite FC and FA and FX over here are my unknowns. And that's good. There's 3 unknowns because you remember we said in 2 dimensions you can have 3 independent equilibrium equations. So it's a well-described problem. Okay, so here this is just redrawn. This is the same information as I wrote before, although I hadn't yet added here the F due to the load. Now I'm just going to rewrite these where my F1, remember this time F1 was that the load of the bar or the beam, so it's 30 kilograms times G, and F2 is 50 kilograms times G, and those are known. But to clarify my unknown, they are the ones right here. These are my unknowns. Now at this point, you notice that before I had the FXA here, and now I've left it out. And the reason is, if we look at this diagram on the left, there are no other forces in the x direction. And that tells us right away that we can, without going any farther, say that that means that Fxa is equal to 0, because we know that it, summed with any other forces, have to equal 0, and the other forces are 0. So it's fine to do this with little or no explanation, to leave out unknown support reactions once you've seen all of the loads on that you know are 0. So we're now down to 2 unknowns, and we'll have to write 2 equilibrium equations. So preparing to write the equilibrium equations, I have my free body diagram. I've established already that my unknowns are these two, and that F1 and F2 have known values. So I'm going to first write my equilibrium equation in the y direction, because I know that students in my class are more comfortable in writing equilibrium equations for force, whereas the other ones are new this year. So the equilibrium equation to force, I say the sum of forces in the y direction is equal to 0 because it's at equilibrium, and now I add them together. So F1 is pointed downward, and so it'll have a negative here. F2 is also pointed downward, so again negative. FA and FB are pointing upward, so they're positive. And note that I haven't confirmed that those support reactions really are pushing up. There can be situations where, as probably all of you know, you can have a beam across two things, and if you step way over to the side of one of it, part of it can go, the other end can go whipping up. So it is possible that they're not pulling it down, that they're not pushing upward. They might be pulling downward, but we always define them in the positive direction. So the positive direction, the unknowns were defined that way, so those are plus. So we are not ready to solve this equation because, as we've already established what the unknowns were, we notice it has 2 unknowns. And so we're going to need to do something else before we can solve it. So our next step is to write the equilibrium equations for moments. And so I'm going to pick the location of the moment at one of the unknowns. So in this case, I'm picking it at this point here where FA is 0. And I do that, the y here is I do that in order to have no unknowns, or to take that one out of this equation. So FB should be the only one unknown in my moment equation. And the reason it's 0 when that's the origin is because that force, if that's the origin, goes right through that. And so it doesn't create a moment when it goes through, when the force goes through the origin. So now the rest of them do, and I like to draw it this way. Some people, a lot of my students can do this in your heads, but if you find you don't do it with pretty well close to 100% reliability in your head, I recommend doing a technique like I do. So I'm seeing the fact when I look at the F1 that I come over here 1.5 meters, and so that's what I've drawn there, and I write that 1.5 in. And then there's this force going down here of magnitude F1. And so I just draw that, and it doesn't matter which way, but I like drawing it where the F vector goes from the R vector. Now I can put my hand across that And by the right-hand rule, I get that negative there. And so I just remind myself that that's negative. And then I go to the second one, and the second one's the same thing, but now I go all the way here to the F2, and that was 2 meters. And again, it's negative. And then last, I go all the way out the 3 meters, and now this time it points upward at FB. And now I can just take those, and I'll say the negative gives me that. And the 1.5 comes in here, the F1 in here. And then here again, negative, and the 2 meters times the F2, and then plus the 3 meters times FB. Sorry, this came over to the bottom over here. And so now I can just rearrange this equation. I bring it down here to rearrange it to solve for FB. So I'm going to have to divide everything by 3 meters. So, and then I also am going to have to change the sign of everything but FB. FB is positive here. I want it to stay positive. So I'm putting it over here, dividing by 3 meters, and switching the sign. So minus 1.5 times F1 becomes plus 1.5 divided by 3 is 1/2, and that's this one right here. So we go from that 1.5 there, comes to this one here. And then the minus 2 times F2 becomes plus 2/3, because 2 meters divided by 3 meters times F2. And that's all that was there. So that was my new equation. And now I'm just going to plug in the values. I'm approximating here that G is around 10 meters per second squared. And so that's why these are, F2 becomes 500 and F1 becomes 300. And so the total is 333, which was 2/3 of 500. 150 is 1/2 of 300. And the total value is 583. And I should take a moment to say, we know it has to be newtons because forces were newtons, but I should go up and error check this, that the units here are kilograms meters per second squared, which you can confirm is a newton. That's always good news. So that's my value for FB. Great, I got FB out of my moment equation. Now to get F1, I'm going to come back to the force equation and plug in that new value for FB. So FA, first I'll rearrange this, is negative FB, because if I put that over on this side of the 0, it's negative FB, and then it'll be plus F1 and plus F2. That's what I get here. And I should say this thing right here is just referring to sum of forces. It's just a conceptual thing. There's nothing in there I'm actually subtracting out here. In fact, they would all sum to 0, and so it's just, this is the sum of forces, is what that means. So that thing being there is irrelevant. I'm just adding them to the other side of this 0. So then I can plug in these values, and they're all in newtons. I had the value of FB, the value of F1 and F2 from up here, and then I add those together and I get 317 newtons. So they're both positive, which doesn't tell me anything's right or wrong. Remember, I defined them in the positive direction out of convention, not because I thought they'd be that way, but let's go ahead and error check. So the support reactions have units of newtons. That's good. Then both of them are positive, and that pretty well makes sense because we're balancing the downward weights. And unless you have something sticking off the end and a weight there that could pull up at the other end, like something down here might pull that one up, they're not going to be negative. And that's the kind of intuition you gain after a while. And then also notably, FB is higher than FA, and that makes sense because this person is closer over here, so more of their weight gets distributed onto here. Again, intuition that might make sense at one point. So all of it makes sense so far, and we got a solution. We were able to use our free body diagram to write our equilibrium equation.